Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Today, I'm delighted to say I'm joined by Lawrence Kuiper, who'll be talking about his ICDE paper, These Rows Are Made for Sorting, and that's just what we'll do. Lawrence is a PhD student at CWI in the Netherlands, and he also works at DuckDB. Lawrence, welcome to the show.
Hi, thanks. Thanks for the intro, Jack. Happy to be here.
Fantastic. The pleasure's all ours. So let's jump straight in then. So maybe you can tell us a little bit more about yourself and how you became interested in data management research.
Right. So I'm 27 years old, living in Amsterdam, and as you said, working at CWI and DuckDB. And I did my bachelor's and master's in computer science in Nijmegen, where they don't really do much data management. So we do some modeling, some SQL, but we don't really know how the database actually works. And luckily, I had a professor there, Arjen de Vries, who worked at CWI for 15 years. So he knows Hannes, he knows Peter from CWI, and he really likes data management. And I got to know him through a course on Spark, and started talking with him, and eventually did my master thesis with him, and got interested in data management that way, which is a miracle because there's no data management in the master's there. I did a bunch of machine learning in my master and got really bored of that. So I'm really happy I got to meet him, and I'm really happy I ended up in the data management area.
Fantastic. And now you work for the coolest database startup in the world as well. So that's that must be fun, right?
Yeah, I'm really happy to work for DuckDB Labs as well. So we've been a startup for a bit over a year and a half now. And we're a small team, about 15 here in Amsterdam. We have some remote people. And it is really fun to work for such a young company. But we're getting a lot of traction on GitHub and on Twitter and in the data science space. So it is very fun to work here.
Awesome stuff. Well, let's talk about sorting then today, what the focus of your paper at ICDE was. So maybe you can give us some background. I mean, sorting, it's kind of a classical topic in computer science, right? But maybe you can give us some background about the context of sorting in relational database management systems, and just kind of generally give us the sales pitch for your recent paper.
Yeah, of course. So sorting kind of seems like a solved problem, right? At least if you search for sorting algorithm on Google Scholar, you'll get about 2 million hits. So it's a very well researched topic, and everyone, of course, learns about it. The n-log-n sorting algorithms in their computer science degree, but this sorting algorithm research tends to focus on a few use cases that don't really translate one-to-one to database sort or sorting relational data. So they tend to focus on large materialized arrays of, let's say, integers that are just sitting there in memory. And then they just try to sort them as fast as they can. Or there's another field within sorting where they have these large distributed sorts where they sort petabytes of data. This is a bit closer to the data management or like the relational data sorting. But for relational data, you sort on multiple keys often. So you can order by all of the columns, ascending, descending, and you also select other columns. So it's very often the case that you select 10 columns and order by just one. So there's a big difference between that and sorting algorithm research. And that's why I chose to research this. Also, we needed a good sort implementation for DuckDB, right? So that's a good motivator as well.
Awesome. Cool. So yeah, you kind of touched on it a little bit there about the challenges of implementing sorting in relational DBMSs, but like how hard is it to take the existing sort of like the huge amount of like existing literature on sorting and then applying that to and implement that in a relational database? What are the kind of challenges there?
So if you just want to get it to sort, then there's no lot of challenge. So you can materialize your data and call sort. And we implement DuckDB in C++. So the sort API is just you give it the start of the sequence to be sorted and the end and the comparison function. The thing is, you can apply any sorting algorithm, but it probably won't be fast. So that was the real research in my papers. You can get PDQ sort or whatever like state of the art sorting algorithm, but the API tends not to be good enough because you pass it this comparison function, and if you ship a compiler with your database like Hyper and Umbra, they use a compiled execution engine, then this is great because you can compile in the data types and you can compile in the comparison function. But for interpreted execution engines like DuckDB, we don't ship a compiler, and we cannot compile in the comparison function. And then you get dynamic function calls in your comparison function. And for vectorized engines, you usually amortize the overhead of these dynamic function calls by calling them once per vector. And then it's really not so much of a big deal. But this comparison function, you do it n log n times. And then the dynamic function call overhead tends to become a huge cost. And that's why you can't just call std sort or pdq sort in your interpreted database system, interpreted execution engine.
Cool. So before we continue, could you maybe explain the difference between a compiled query engine and an interpreted query engine?
Right. So this started around let's say the 2000s when, of course, database systems are an old topic, right? And we have the classical OLTP style database systems, which have generally an interpreted execution engine. So that means these systems really pull one row through the query plan at a time. So let's say you have a table scan and then a filter, and then that's your query. Then they pull one row from the base table through the filter and then to the query result. And this tends to then you get a dynamic function call for the for the filter evaluation for every row that you pull through the query plan. And around the 2000s at CWI, Peter and Marcin invented vectorized execution where you pull one vector through at a time. So let's say the vector could be 1,000 or 2,000 rows at a time. And then the data would be in a columnar format instead of a row format. And this really, really speeds up. This is the dynamic function call overhead is one of the reasons that this really sped up query processing because you're doing less dynamic function calls. There's also SIMD and cache locality. I won't get into that too much. And then you have compiled execution engines. And the compiled execution engines also deal with the same problem by just-in-time compiling the query plan. And then by compiling in stuff like comparison functions and data types that perfectly fit the query types, the types that are expected in the query, you also get no interpretation or dynamic function call overhead for these tuples flowing through the plan.
So you said there that kind of things are not fast if we're in an interpreted execution engine, we use the kind of off the shelf PDQ and stuff like that APIs. So you did a micro benchmark where you wanted to kind of compare the differences between, I don't know, having a row versus a column data format and then sorting in these two different types of query engines to see guess what came out best, what was the best way of doing this. So can you maybe walk us through the design of this experiment and how you set it up?
Right. So I tried to make it as simple as I could and make it isolate the raw sorting performance there just to see the characteristics of columns and rows. And what I did is I generated a few different data distributions, so a random distribution and some correlated distributions. And I generated fully materialized columns of data or rows of data. And the rows would have all the data tightly packed together. And I would interpret it as a C++ struct. So this was actually a compiled approach because in the micro benchmark, I don't have to interpret types because it's just my micro benchmark. There's no actual queries. So I could just compile in the types and then see the performance of sorting just rows or just columns. And then we basically isolate the memory access pattern of sorting rows and sorting columnar data, and also the branch predictions of the comparison function of these approaches. So that was the setup. And then I sorted it. So one of the points I tried to make in the paper is that it doesn't matter what sorting algorithm you use, because we're trying to see what the rows and columns do, right? The the sorting algorithm doesn't matter as much. So I just went with std sort, but I did cross-validate with std stable sort because these are quite different. So std sort is a introspective sorting algorithm, is mostly quick sort, and stable sort is a merge sort algorithm. So these have quite different cache or like memory access patterns.
Okay, cool. So let's talk some results then. So there's two different ways you use of actually comparing kind of tuples, right? And then you kind of in your paper you talk about them for how it was for sorting columnar data and for row data. So let's start off with the two approaches, then we can talk about columnar data, right?
I looked at two approaches to sort. Like generally, you would think there's only one approach to sort because you're comparing rows when you're sorting, and there's only one way to compare a row, which is just to compare the data in the first column, and if they're equal, then you have to compare them in the second column. And you keep comparing the values in the rows until you have a value that's not equal, or until you've compared all values in the row. And I called this the tuple at a time approach. But there's also which some database systems implement this columnar data format while sorting. And these tend to go for the subsorting approach, which I call the subsorting approach. And there they sort the data by the first column. So let's say you have multiple columns in your order by clause. They sort all the data by the first column. Then they identify which rows are tied, so which have the same value in this first column, and then have like this small sort on the second column for just these rows.
So what were kind of results then for sorting columnar data then? So how did it fare?
So the subsorting approach is quite clearly better for sorting columnar data. There's some maybe so for the merge sort, the tuple at a time and the subsort approach were quite similar, but in general, the subsorting approach is better because you simplify the comparison function because you're only sorting by one column at a time. So your column is just this value is less than that value instead of looping over the columns in the order by clause. And secondly, it's also more the memory access pattern is better because you're only accessing this one memory region at a time, which is this one column, and then you move on to the next column. So if you would do this tuple at a time approach for columnar data, you compare by the first value, by the value in the first column, and if they're equal, you have to compare by the value in the second column, and that's random access into like a different memory region, which slows down the sort. So the subsorting approach was better here.
Okay, and I'm guessing this flipped around for the row data.
So for the row data, interestingly, it didn't flip around. So the subsorting approach, you end up doing less comparisons in total.
Okay.
Because often you don't need to loop through the whole row to get the full comparison, and somehow you end up doing slightly less comparisons. And the memory access pattern, there were slightly more cache misses for this subsort approach because for the row data, the data is co-located in memory already, and the memory access pattern is excellent already. But somehow it was slightly faster still, this subsorting approach.
Oh, that's fascinating. So obviously, this micro benchmark kind of focused primarily on how he was laying out data. So how did the type of query execution then sort of impact sorting? So this wasn't included in the micro benchmark, right? This was like kind of more of a discussion section in your paper. So maybe can you elaborate on the impact of the execution engine?
Yeah, so the execution engine mostly impacts how you should compare tuples. So how you should compare your rows. So it's quite clear from the micro benchmark that you should use rows regardless of your execution engine. But how you should compare tuples. So for the compiled query engines, it's simple. You compile in the comparison function, and that's about it. Then you have an efficient comparison function. But for the interpreted execution engines, you get dynamic function calls, and this greatly slows down the comparison. So what I ended up doing is something that was invented for System R already. So it's quite an old approach, but somehow, of course, there hasn't been much research on sorting relational data, but somehow this approach got lost. And it's to normalize the values, normalize them so they are sortable as if they are strings. So for integers so generally computers use big endian architecture. So the most significant digits are on the end. But if you sort a string, the most significant digits are in the front. So what you end up doing is swapping all the bytes. And then if it's a signed integer, you end up flipping. I think you end up flipping the bit. Yeah, you end up flipping the sign bit so that the negative integers come last. For strings, of course, they're already good. And as it turns out, you can do this key normalization, this string comparison for floating point numbers as well. You can also encode them so they are comparable as a string.
Fascinating. So, I mean, it's mad that like System Arm, they did so many things in System Arm now. Like, it's crazy, right? It's like, I'm sure pretty much they did everything you could possibly ever want to do with a database in System Arm way back then. And yeah, it's crazy. Sure. Sorry, where was I with my question? So yeah, so maybe this isn't a valid question, but you said that rows is always the best. But is there sort of like is having rows with a compiled engine better than having rows with a interpreted engine, for example? Or does it kind of like what the interaction effects of these two dimensions is? Because I guess what I'm asking.
No, I think it's a good question. So for interpreted, so so I can give you one answer straight away, and that is as the input size grows, if you have a large input, if you're sorting more data, then it's a no-brainer. You always use rows, and there's no real discussion there. For the interpreted execution engine, sorting by one column at a time, I think would yield more benefit. So using this sub-sorting approach would use more benefit because you don't get this interpretation or function call overhead. And for the compiled execution engines, they get a lot more freedom because they don't have to deal with a lot of this interpretation overhead while sorting, because they can just compile in the comparison function of the data types. So for the compiled execution engine, just go with rows. Always go with rows. Okay. And compile your comparison function and enjoy your fast sort. For the interpreted execution engine, I'd say also go with rows because you don't know how large the input is if you have a streaming engine, right? So there's data coming in, you have to materialize it to sort. So just go with rows anyway. And then it's up to you. Do you want to compare rows at a time? Well, if you want to compare like whole rows at a time, you might want to choose for this key normalization approach that I just discussed, where you compare the rows as if they're strings. And or you would use the subsort approach where you compare by one column at a time and then don't have this interpretation overhead for every comparison.
Yeah, what's the sort of the overhead in terms of like it's laid out on disk in columnar format and then materialize it into rows for when you want to do your sorting? What's the sort of overhead there? How costly is that, doing that transformation to then convert it back to columns at the end?
Yeah, so that's a good question. So that's of course there's a cost, but this cost is actually quite low. So
okay,
if you have a streaming engine, you have this what we call data chunks coming in. So there's vectors of data coming in, and these are like the in-flight representation of data. And you can't just say, oh, here's my data chunk, I'll store it somewhere. You have to copy the data over to buffers. You have to actually materialize the in-flight data coming in. So if you have to materialize anyway, then you have an option. You could go to columns or you could go to rows. So you're copying the data either way. I'd say go to rows because it pays off. Yeah. And the cost here is not that high because instead of copying one row at a time, you copy one vector at a time. So let's say you have 2,000 rows, you copy the first column, so that's the first vector, copy it into the row, and then the second, and then the third. And what you end up doing is very much so the data is in L1 cache all the time. Yeah. And there's just purely sequential access. So it ends up not being restrictive at all.
Nice, awesome. Because I remember when I first sort of was reading through the paper, and in the introduction, you have that sort of example of kind of going, it's even better if you go from columns to rows and back again. I was like, really? But no, when you kind of like dig into it, it makes sense, yeah. But it kind of initially was sort of counterintuitive to me. But no, that's really interesting. So, I mean, the kind of the next step in your paper was sort of tying together all of these existing techniques that already existed in the literature, and then in the context of an interpreted query engine, I guess because this is going to be implemented or was implemented in DuckDB. You have a nice section where you tie these all together. So can you maybe tell us about some more about these techniques and how you managed to tie them all together, and walk us through what you found here?
Yeah, so I ended up implementing this in DuckDB. So the first step is we use the sort is fully parallel. This is important for any database system now. If any part of your system is not parallel, it doesn't keep up with the rest of the system. So you need to parallelize every step. So we use morsel-driven parallelism for this, which is a paper from 2015, where the parallelism comes from chunking the inputs. So let's say you have a table scan and it's 10 million rows. You partition it into inputs of around 100K rows. And then each thread scans 100K rows. And when they're done and there's still 100K rows left that haven't been scanned, then they get that. So that's kind of a data-driven parallelism. Okay. A lot of systems before used to use some different kind of parallelism based on some hashes or whatever, and with the exchange operator. But this doesn't scale well. We have now parallelism aware operators, and we have the morsel-driven parallelism. Okay. So let's say every thread is scanning data. Every thread gets data into the sort operator, and then each thread materializes that data into the row format. And then when there's no more data left, we're done converting all the data to row format. Each thread sorts the data that they collected. So this should, given the morsel-driven parallelism, each thread should collect roughly the same amount of rows, give or take 100,000, but it's not so big of a deal. Then let's say we have 4 threads, then we have 4 sorted runs. And so this initial sorting step happens in DuckDB with either radix sort if there's integers, or PDQ sort if there's strings. And as I said, you can't just use the PDQ sort API as is. So luckily it's open source, so I was easily able to modify it so that it was efficient for our data layout. And then let's say we have 4 threads and we have 4 sorted runs. Then we start a merge sort. Merge sort can be tricky to parallelize. There's 2 kinds of merge sorts. You can have a 2-way cascaded merge sort where you keep merging 2 runs and 2 runs and 2 runs until you have only 1 run left. Or you have this K-way merge sort where you use something called a tree of losers, where you merge all 4 runs into 1 run at the same time. I ended up going with the 2-way cascaded merge sort. I have some regrets. I want to go with the K-way merge sort, but I'll explain later. So
sure, yeah.
We go with a parallel 2-way merge sort, and this can be tricky to parallelize, right? Because 1 thread can merge 2 runs. But what if you're down to your last 2 runs and you have, let's say, 48 threads? You would think that only 1 thread can merge those 2 runs, but you can actually pre-compute partitions of that can be merged independently and therefore in parallel. So with binary search, you do a binary search through the 2 runs that you're going to merge, and you find a point where you're sure that the next comparison would either copy the right run and then the left run. So that's kind of like an intersection.
Okay. Yeah.
So this is a paper called Merge Path that explains this, and you kind of compute some intersections between the sorted runs with efficiently with binary search, and then you can merge parts of the run in parallel, and that of course greatly speeds up the process. There's some work you have to do, but in return you get parallelism, so that's worth the effort. So you keep merging until you have only 1 run left, and then you are done and you scan the data from rows to columns again.
So let's dig into the K-way, and when you wish you'd done that one instead, why was that? I mean, is that just because it's more fun to implement or more interesting, or was it actually like a performance-based reason as to why?
Yeah, so I've learned now that so the sort in DuckDB is very fast, but if you select a lot of columns, so let's say you select a very wide table, you have 10 columns, you're only sorting by 1 column, then with this 2-way merge sort, so the way I implemented it is, what you can do is you can sort the columns in the order by clause and then collect all the data in the the other selected columns after you're done sorting, right? And that would be the most efficient way, because then the payload, like these other selected columns, just sit there. They don't move through memory all the time. However, if you want to sort more data than fits in memory, then you cannot do this anymore. Because let's say your data is 2 times the size of memory, and all these columns that you selected but are not sorting by are just sitting there, but they have to go to disk. And then you sort by the key columns, so the columns in the order by clause, and then you have to collect all the rows in the right order, but they're on disk and in memory. And then so if your data size is big enough, your random access to memory becomes random access to disk. And at that point, you're screwed, because the performance just plummets. So what I ended up doing is that you don't collect it at the end. So you don't collect the payload data at the end. You just keep merging it through. So then you have sequential access, and you don't have random access to disk. But I chose to do the two-way merge because I knew how to parallelize it.
Okay.
And we needed a parallel sort because, as I said, you cannot have some single-threaded thing in your parallel system. So I regret this now, because I know that copying the payload throughout the merge sort is very expensive. So if you have a lot of other selected columns, then this becomes actually a performance bottleneck. Okay. And for this k-way merge, I think I figured out how to parallelize it. I didn't know how to parallelize it because there was no related work on this.
Okay. So there's a follow-up paper there, I'm sure, when you...
Yeah, possibly. So I haven't touched sorting in a while, but I think I figured out how to generalize this idea of merge path to a k-way merge. I haven't found any work on this, but I think I know how to do it. Nice. Yeah, I think if you look at the two, anyone can connect the dots. It'll take you a while, but I've thought about this a lot.
Waking up in the middle of the night thinking, I've got it.
Yeah. This happens to me every now and then. So I think I know how to do that. But I'm now onto like joins and aggregations. Okay. So it'll be a while before I touch sorting again. So yeah, we'll see.
So you see this is a question more on like how. Or like, what's the tipping point between me selecting too many columns and it becoming a performance bottleneck? And versus how often do you see people doing that? Because I guess a lot of the work in DuckDB is driven by kind of what users want, right? So I guess it's like, how high up the priority list would it be to sort of cater for these selecting large number of columns?
So it's actually, for the use case of DuckDB, it's not a big deal. Okay. It's just something I want to do because some users run into problems here. So we can sort more data than fits in memory, but usually DuckDB users tend to have data that fits in memory. But one of our goals is to have DuckDB be like some kind of mini Spark cluster, right? Like your MacBook with incredibly fast SSD can utilize disk really well during the query execution, and you'll be able to skip Spark because we don't like Spark, and you'll be able to use DuckDB instead to do larger than memory processing. And for sorting, so sorting shows up in window functions mostly, right? And maybe some inequality joins, but most people see them in window functions, and we don't really get many requests or like issues for people who have window functions that don't fit memory. And the rows tend not to be that wide, but every now and then there's someone who says, hey, so these people just benchmarking DuckDB and whatever, using it for whatever it wasn't intended for, but people generating TPCH scale factor 100 and then trying to sort line item.
Right, okay.
And then they say, hey, this is very slow or this doesn't work. And I think I can make that very fast, but I need some time
to
implement that.
Cool. That's going to be, I'm sure that'll be interesting when you get around to it for sure. So I just kind of briefly want to touch on implementation a little bit. And obviously, you're very sort of like well versed with how like DuckDB is sort of architected and built. So I guess the implementation of it for you, I guess what I want to ask is, how much of an undertaking was it to add this new sort operator in?
So So I did this when I wasn't well versed
Oh, okay,
in
right. So this
DuckDB.
is your first sort of like
This is the
hurrah into it. Yeah, yeah.
Yeah, this was the first physical operator that I touched in DuckDB. So I'd done some scalar functions and I implemented macros in
Right.
DuckDB.
Okay.
So then you can like create a SQL expression as a function. And this is so I touched a little bit of physical execution, but not an actual operator. And the sort operator was one of the last operators that had a very basic implementation. So the join and aggregate were really optimized and well refined, but the sort was something Mark wrote in 2 hours. It's just
Right. Okay.
something so it worked, but it wasn't so it was fast. You need more time to write something fast. So this was for me a huge undertaking because I had to learn the parallelism, the model of the Morsel driven parallelism. A lot of that is abstracted away behind a nice API, but I had to learn a lot of things about parallelism and locks and atomics that I didn't really know. And I also had to learn how to use the buffer manager well, because I also had not had to touch this with my previous endeavors in DuckDB. So for me, this was a huge undertaking.
Yeah.
It took many months to implement this. I think if I would do it again, then I could make it faster in less time, right? But I'm now like years, like a year and a half. It's a year and a half after the sort went into DuckDB, so I've learned a lot, and I could do it better now.
Yeah, for sure. Yeah. Well, I mean, you need to have that initial sort of, you need to go pay that initial sort of pain, right, to get to the point where you are now, where you could do it easier, right? So yeah, that's cool.
Yeah, I'm actually really grateful that Mark and Hannes let me, as like a starting PhD student, just do this, right? I could just implement sorting in their system, and they just trusted me that it would be good. So I'm actually very grateful that I got that opportunity.
Yeah, for sure. Cool. So I guess let's talk about. So you've implemented this in DuckDB, as we've been saying, and you've benchmarked it. So can you maybe tell us a little bit about the benchmarking, how you went about that, and then let's hear some numbers. How fast does it go now versus the initial quick implementation that Mark did?
Right. So I did some benchmarking on TPCDS tables, and also like just random integers, because I just wanted to see the raw sorting performance and then see the relational sorting performance with like multi-key sorting. And I didn't benchmark against the old DuckDB implementation, but this old implementation, I don't think you want to benchmark against it, because it was fine for like sorting 10,000 rows or like maybe 100,000 rows. But as soon as you get to some millions, then you don't know how far the progress is, but it looks like it's stuck. So I think it would take like 10 minutes to sort, or like 5 minutes to sort 100 million integers. Which we can now do in I think it's 1.7 seconds. So
oh wow,
it was terrible, but it worked.
Cool, great stuff. So I kind of I often sort of try and ask kind of about when I'm interviewing people about their work, whatever, like kind of what are the sort of like the limitations to the approach, or like under what scenarios is the performance of whatever it is suboptimal. So I guess kind of putting that question to you, are there any sort of limitations other than the fact that you would, in hindsight, go away and do K-way? What was the name of it again? Sorry?
It's a K-way merge sort.
K-way merge sort. Sorry, yeah. I just wrote down in my notes like tree losers, and that's the word I've got there. I thought it's definitely not called that, right? But that's an interesting, like. But anyway, ignore me.
No, it is. Let me see. So tree of losers is something. It's a tournament tree. So.
Okay.
It's actually the name. So there's something called a tournament tree. I think like many things in computer science, Donald Knuth invented this.
Right.
And it is a way to minimize comparisons when doing this K-way merging.
Right.
So it's a tournament tree where each of the sorted runs goes into one of the entry points of the tournament tree. And then you can have a tree of winners or a tree of losers. And with sorting, we generally think about sorting as doing the lowest value first. Sure. So that's why it's called a tree of losers, because it loses the comparison
I see.
throughout the tournament tree. And so this minimizes the comparisons. And I would, so yeah, that also brings me to the limitation. And I think I already talked about it, but the limitation is really the two-way merge sort requires you to copy over the data. If you want to have an external, like larger than memory kind of sort, it requires you to copy over the data many, many times. For the K-way, you don't, because you're merging all runs into one. You end up only copying it once.
Great. So I guess there's obviously, in an ideal world, you would implement this at some point, but it's not on your kind of immediate rendering. So you're working on aggregations and joins. So I guess kind of that's probably what's next on your research agenda. But like, how is that work going, and where do you go kind of next?
Right. So as I said, one of the goals for DuckDB is to be able to handle larger than memory data gracefully. So it's actually for OLTP systems, because they have been researched for over 50 years now. This is a solved problem they can do out of core, or like larger than memory joins and aggregations, but they tend to have like these small 4 or 8K buffer size, and they tend to be very conservative in their memory usage, while OLAP systems generally don't handle larger than memory joins and aggregations or sorting, and they tend to use up all the memory you have to make the query as fast as they can. And we think that there's a middle ground where we can have fast in-memory performance, and let's say your data size exceeds the memory size by 50% or 20% or 80%, then your performance shouldn't drop off a cliff. So a lot of systems tend to the performance drops off a cliff because they go into this OLTP style, slow kind of larger than memory algorithm, or they just say, "I'm sorry, mate, I can't finish this query. It doesn't fit." So that's actually my PhD topic, is to write like good join and aggregation algorithms for OLAP, for larger than memory OLAP processing. So I've been working on the aggregate and join. So we have a very good aggregate and join implementation, but the data was required to fit in memory. Otherwise, we threw an error. And I've been working on this materialization format. So for joins and aggregation, we also materialize the data as rows instead of columnar format. This is something that is a paper by Marcin and Peter. They found out that this gave also better cache locality for joins and aggregations. And I've been working hard on a materialization format for rows, where the rows have a fixed size. So even for strings, so that means that there's a pointer to the actual string in the rows. But this format can go to disk.
Okay.
So if data goes to disk, your pointers will be invalidated. So we have ways to recompute them on the fly, so that this data can go from disk to memory, and the data stays valid. And this kind of unlocks a lot of out of core potential. So let's say for joins, generally you need the entire build side. So the hash table on the build side, you need it in memory, because you need to make sure that the other side, when you're matching, that it's matched against everything in the build side. But you can partition the build side, let's say, on the hash. So we use radix partitioning, and then that relieves some memory pressure. So you pin a few partitions in memory, and then you probe against that during the probe of the hash join. And we use the exact same row format for the aggregate as well. I haven't touched the aggregate too much. I've just implemented the row format in there. But for the join, we are already fully support larger than memory. And so next steps for me are tweaking that until the performance is satisfactory, let's say. And same for the aggregate. And I spoke to Thomas Neumann at ICDE, and he described an excellent optimization for hash tables that I'm also going to try to implement.
Fantastic. The next question I often ask is kind of, how can a software developer and engineer sort of leverage the findings in your research? But I mean, and kind of like what impact do you think it can have? But I mean, with it being in DuckDB, I guess it's having real world impact now. So I guess I'm going to rephrase it a little bit and say, like, what impact have you had so far? And have you had any feedback on kind of the performance of the new sorting operators and and what's that looked like? Are you just saying this is amazing, fantastic, changed my life?
So we've had some positive feedback from, so this has been in DuckDB for a while now, but we've had some positive feedback from people who were happy that they could now sort large data sets, because this was really like prohibitively expensive before. But of course, it's also led to people, as I said, generating TPCH skill factor 100 and then sorting line item and then wondering why it's so slow. Well, so these issues are then for me, because I implemented the sorting. So there's been some positive feedback, but of course also some negative feedback. But the negative feedback has been quite minimal, because in general people don't sort at like many gigabytes of data. So it has been good, but in general with operators in database systems, people expect them to be good. So you generally don't hear much. So of course we get the most feedback from GitHub. You don't hear much. You only hear about, hey, my join is slow. Hey, my aggregation is slow, right? So I've received much more positive feedback from something like, I implemented the JSON extension for DuckDB, and we can now directly read JSON files as if it's a table, right? So you can do select star from, and then your JSON file.
Right. Okay. Cool.
And we have rich support for nested types, so list and struct, and these map well to the JSON arrays and object. When I implemented that, the positive feedback was much more than I ever had for the sorting, because people were like, "Wow, this is some shiny new functionality," and whereas for sorting or joins, they're like, yeah, this should work.
That's smart, did it really? Yeah. I mean, it must be really nice to get some feedback kind of at all, I guess, on your research. I mean, kind of, I guess the average sort of PhD student, I don't know, I'm probably speaking from my personal experience here more maybe, but like you write a paper and no one ever really looks at it ever again. So to have your work go straight into a system that like thousands of millions of people are using, then it must be a really nice, rewarding experience, for sure.
Absolutely, yeah. That's very motivating, actually. Just to think about, hey, I want to get this stuff in before the next release. That's a huge motivator for me.
Yeah, cool. I mean, whilst you've been working on sorting, from that sort of journey, initially starting on the project, were there any sort of things that were kind of interesting or unexpected that you learned while working on sorting?
Yeah, so I initially so this lesson I learned while sorting is I initially thought I would be able to take the best sorting algorithm that I could find and just apply it to my data, because I thought sorting also I thought of sorting kind of as a solved problem, right? And the more I tried to find papers on relational sorting, I was very surprised that it wasn't. So I tried this a few times with different sorting algorithms. I found that we were so just using the std sort API, but then with something like block quick sort or PDQ sort, I found we were a lot slower than MongoDB. And of course, we want to be faster than MongoDB. So I was quite surprised with this. And then I really learned that you have to implement the sort yourself for your data structure. For like it's not a compiled thing or an interpreted engine, so you have to really, and that was very surprising to me. And then all the way in the end, like I said, this cost of mem copying the rows around through the two-way cascaded merge sort, that was also something that I found very interesting, because that's purely sequential access, right? During the merge sort, you're purely doing sequential access, copying the rows around. And I thought that would not be very expensive, but it ended up, for if you have a very wide table, ended up being much more expensive than I thought. And at some point I will implement this K-way merge sort,
to get rid of like vendetta now, like a mission. I've got to do this at some point. Yeah,
absolutely. Yeah. I have to.
Yeah, fantastic. I mean, the next question I often ask people, I guess we've maybe touched on a little bit, and kind of things that you try along the way, like you mentioned a second ago, that you can't just take something off the shelf and apply it and it work. But are there any other sort of, like, I guess, like war stories from working on this, that things that were like tried and failed?
So stuff that tried and failed. So I first implemented just sorting and memory sorting, and then I made it go larger than memory. And I had my own row format just for the sort. And the rows weren't fixed size, so they were variable size. So the strings were just in there. And kind of at the same time, Richard, one of our remote contributors, he started unifying the other code where we had rows that are fixed size, right? So he wanted to unify every place in DuckDB that we were using rows, because we were using these solutions that are just in every operator instead of having like this unified framework of going to rows. And I ended up like scrapping my row stuff and then using his row stuff. And then there were pointers in there, so I had to figure out how to deal with that. And my approach was pointer swizzling. So instead of the pointer, you can overwrite it with an offset before it goes to disk. And then you can recompute the pointer when it loads back into memory. And that's what we have in most operators now. But that is very tricky to get right, because you have to keep track of, is this a pointer or is this an offset? You need to have some serious bookkeeping everywhere. And then at some point, Mark implemented this column format, or like column materialization format. And this also had the problem that there were pointers in there. And then I figured, hey, you don't actually have to go from pointer to offset. You can just load the data back and then compare the pointers. Is the new pointer still the same as the old pointer that was stored there? Okay. If it's not the same, you can recompute it on the fly without ever going to this offset. And having learned that from the column, like materializing data in a columnar format, I immediately applied this to this new row materialization format that I've just implemented. And this is really nice, because if the data doesn't ever go to disk, then you've never touched this pointer and made it an offset. You just compare one pointer and see, oh, the pointer is still valid. We can scan this. And that's like, that was a huge lesson. So that took actually, let's say, 2 years to realize that this is the way to go.
2 years.
Yeah, I had many iterations of this, and we've now realized this is the way to go for us. So
it's been worth it in the end. Then it's been a long journey, but it's paid off.
Absolutely, yeah.
Fantastic. Well, I've just got a couple more questions now. But obviously, all of your work kind of goes into DuckDB. But other than sort of the joins and the aggregations, are there any other sort of things you're working on, or like your other research that the listener might be interested in hearing about?
So the joins and aggregates, the out of core stuff is my main research, but I don't really have a time for side projects.
I can imagine.
In research, but I do have side projects in DuckDB, right? So the JSON extension was a huge side project for me, and I had a lot of fun doing that. So if anyone has like a lot of new line delimited JSON lying around and they want to shred through it quickly, or they just want to try it out, please check the JSON extension. We have a blog on it. And I want to give a shout out to the author of the open source JSON library that we use. So we use the YYJSON library, and it's written in C89. So it's very portable, but it's also incredibly fast. And we, of course, want to have portable software as DuckDB. So this author is really awesome, because I requested a change because I really needed this for the DuckDB implementation. That's had to do something with allocations. And he said, well, I could, but that's a breaking change. Okay. And then one day later, he said, okay, let's make the breaking change. And then he changed the API for us. It was... It was really useful and made our JSON allocations much more elegant.
Oh, amazing. So, that's awesome. So you said that you don't really have like much time for kind of side quests other than sort of things within DuckDB. But how do you go about like deciding those things, like working on the JSON extension, for example? How do you actually approach saying, okay, this is a cool idea to work on, and then just saying, okay, yeah, I'm actually going to dedicate some time to this?
Yeah, so I think I started on the JSON extension about 1.5 years ago, and I did it just because I thought it was fun. So I saw this YYJSON library and I was like, yeah, this is perfect. let me try to write some JSON functions in DuckDB. And I basically copied what other systems have, right? Because people expect a system to have those functions. And I had some basic functionality, and then I didn't touch the extension for, let's say, a year. And so that really was something that I was interested in. But then, of course, since then the company was founded, and of course, then money starts dictating what you work on. So one of our clients actually requested this, and I went into JSON again and made us be able to read. But our clients, so it's not like they pay us to implement this functionality. It's also for our clients, we have clients that have a common goal, right? We want to make DuckDB better, but they want to use DuckDB for a specific use case. So we collaborate, and then we try to make the best JSON processing that we can. And then we're really happy with it because it ends up in the open source project and everyone can use it. And then they're happy with it because they wanted this feature specifically.
Ah, okay, cool. So it's like kind of like they almost like sponsor the work in a way, I guess. Then I don't know if that's the right way to thinking about it, but like it's like
it's kind of sponsorship, because it's open source, right? We don't make tailor-made stuff for them. It's it all goes into the open source project.
Fascinating, fantastic stuff. Yeah, and long may that continue. Cool. So just two more questions now. So the penultimate one is it's kind of a big picture sort of question. So it's, what do you think is the biggest challenge in data management research today?
Yeah, I think this is a very, very tricky, very tricky question. So I'm very absorbed in my own research. But what I saw at ICDE is, I think one of the challenges is this scale up versus scale out question. And the CEO, or not the CEO, the lead engineer at Google BigQuery, who's now the CEO of MotherDuck, is Jordan Tigani, and he saw that about 90% of the queries in BigQuery accessed about 100 megabytes of data. And of course, we need these large distributed systems because sometimes we have analytics that are much larger than a single system can handle. But I feel like in data management research, there has been so much focus on this distributed system that there has not been enough attention for the single node. And I feel like some of the researchers don't realize that we really need this single node, because 90% of the queries don't need the distributed system, and we shouldn't be using the distributed system because it costs more money. It uses a lot of energy. It's often slower because they assume that the query will be a large distributed query, and then it ends up being a small one, right? So, of course, I also say this because we have a nice single node system, but for me, that seems like something that's quite important right now.
Awesome. Yeah. So I guess last question now, last word. What's the one thing you want the listener to take away from this podcast episode today?
The one thing. Okay.
You can have two things. You have as many things as you want.
No. I think the one thing. So for me, this journey of researching sorting is, don't ever make the mistake of thinking that something is a solved problem.
Okay.
And in the end, the solution for me wasn't very difficult. It was use rows, use this technique from System R, right? But this combination of techniques that were already there, but that had not been researched well, like, for example, join algorithms, which have been researched a lot. This combination of techniques that may not seem very novel ended up being very effective and something that was not researched before. So if there's any researchers thinking that, hey, I can't research sorting, it's been beaten to death, let's say, probably not. There's still some stuff to do for you. You can still research that.
Fantastic. That's a great message to end it on. So let's finish things there. Thank you so much, Lawrence, for coming on. If the listeners interested in knowing more about Lawrence's work, we'll put links to everything in the show notes. And if you enjoy listening to the podcast, please consider supporting the show through Buy Me a Coffee. And we will see you all next time for some more awesome computer science research.